Hi, this is Geeta from VIT University. I'm here to discuss on the topic DFA minimization. DFA minimization is the process in which you convert a complex DFA to a simpler DFA. This is the deterministic finite automata consisting of 8 states. The starting state is Q0 and the final state is Q2. We are going to minimize the DFA using the table approach. So we have to draw a table similar to this. The first step in DFA minimization is to remove all the invalid entries. The tuple set consisting of same states like Q0, Q0, Q1, Q1 are considered to be invalid and hence they are removed from the table. The second step in DFA minimization is removing the duplicates. Here, Q0, Q1 and Q1, Q0 are considered to be duplicate sets and hence the duplicate set of Q0, Q1 is removed. This is done for all the duplicate sets. Hence, half of the table is considered to be invalid. Then we are going to mark the final state, which is Q2, as in our problem. The step 3 in DFA minimization is to mark all the combinations of final state and non-final state. So as we have marked our final state Q2, we can easily remove all of its combination with the non-final states as shown in the table. This is the transition table for the above problem. We have marked all the states Q0 till Q7 and the input variables 0 and 1, and we have found the transition function for these states. So our step 4 is to select a tuple set and we have to find the transition function for those sets. The first tuple set which is left unmarked is Q1 and Q0. So the transition function for Q1 on the input 0 is Q6, which we can take it from the transition table. Q1 for the input 0 is Q6. Similarly, for Q0, the transition function for the value 0 is Q1, which also could be taken from the transition table. So for the input value 0, we have the new tuple set Q6, Q1. Similarly, we are finding the transition values for Q1 and Q0 for the input values 1. So for the value 1, we have the tuple set Q2, Q5, which is marked green already in the table. So if any one of the tuple set is already marked as invalid or not equivalent, then we have to consider the corresponding tuple set, here in this case Q1, Q0, as non-equivalent sets. So we are going to mark Q1, Q0 as X. Now we have to select the next tuple set Q3, Q0, and we have to find the transition function for the same. Q3 on the input 0 changes to Q2, Q0 on the input 0 changes to Q1, and similarly Q3 on the input 1 changes to 6 and Q0 on the input 1 changes to Q5. Now we can see that Q2, Q1 is already marked as invalid, and Q6, Q5, we don't know anything about that till now, but we already have this one marked as non-equivalent tuple set. So we can mark Q3, Q0 as non-equivalent set. The next tuple set that we are going to consider is Q3, Q1. So we have found the transition function for Q3, Q1 for the input 0s and 1s. And for 0, we have got Q2, Q6. And for 1, we have got Q6, Q2. And we know that these Q2, Q6 is marked already as a non-equivalent set. So we can mark Q3, Q1 as non-equivalent as well. The next tuple set which we are going to consider is Q4, Q0. Similarly, the transition functions for Q4 and Q0 is found for the values zeros and ones. And for 0 we have Q7, Q1, and for 1 we have Q5, Q5. Q7, Q1 is still not marked, so we cannot take any assumptions from the tuple set Q7, Q1. And Q5, Q5 is marked invalid, so we can't take it into any assumptions. So Q4, Q0 is left unmarked, and we are moving to the next tuple set, which is Q4, Q1. And the transition functions for Q4, Q1 is found for the input values zeros and ones, and for 0 we got Q7, Q6, and for 1 we've got Q5, Q2. And we very well know that Q2, Q5 is already marked as invalid. So, sorry, it's not invalid, it's not equivalent. So we are marking Q4, Q1 as non-equivalent tuple set. Now we are moving to the next tuple set Q4, Q3. Here we can find that Q4 on input 0 we get Q7, and Q3 on input 0 we get Q2. And for Q4 on input 1 we get Q5, and Q3 on input 1 we get Q6. So from the resulting tuple sets, Q7, Q2 is non-equivalent, so we can mark Q4, Q3 as non-equivalent as well. The next tuple set which we are going to look forward is Q5, Q0. So the transition functions give the values Q2, Q1 and Q6, Q5. We know Q2, Q1 is a non-equivalent state tuple set, so we are going to mark Q5 as non-equivalent state. The next tuple set is Q5, Q1, for which the transition functions gives the value Q2, Q6 and Q6, Q2. And we very well know that Q2, Q6 is a non-equivalent state, so we are going to mark Q5, Q1 as non-equivalent as well. The next tuple set is Q5, Q3, and we've got the values Q2, Q2 and Q6, Q6, which leave us undeterministic about the tuple set value Q5, Q3. So we are leaving this unmarked, and we are moving to the next tuple set Q5, Q4. For the values Q5, Q4, we've got the values Q2, Q7, Q6, Q5, and Q2, Q7 is non-equivalent, and we are going to mark Q5, Q4 as non-equivalent. The next tuple set is Q6, Q0, for which we've got the values Q6, Q1 and Q4, Q5. The value Q4, Q5 is non-equivalent, which we have found just now. So we are going to mark Q6, Q0 as non-equivalent tuple set. The next tuple set is Q6, Q1, and for which we've got Q6, Q6 and Q4, Q2. Q4, Q2 is non-equivalent tuple set, so we are going to mark Q6, Q1 as non-equivalent tuple set. The next tuple set which we are going to consider is Q6, Q3, for which we got Q6, Q2 and Q4, Q6, out of which Q6, Q2 is non-equivalent. So we are going to mark Q6, Q3 as non-equivalent tuple set. The next tuple set which we are looking is Q6, Q4, for which we've got Q6, Q7 and Q4, Q5. And we very well know that Q4, Q5 is non-equivalent, so we are going to mark Q6, Q4 as non-equivalent. And now we are moving on to the next tuple set, which is Q6, Q5, for which we've got Q6, Q2 and Q4, Q6. And Q6, Q2 is non-equivalent, so we are marking Q6, Q5 as non-equivalent tuple set. The next tuple set Q7, Q0 has the values Q6, Q1 and Q2, Q5, Both of them are already marked as non-equivalent, so we are going to consider Q7, Q0 as non-equivalent tuple set. And the next tuple set is Q7, Q1, for which we've got Q6, Q6 and Q2, Q2, which leave us undetermined about the tuple set values Q7, Q1. So we are leaving it just unmarked. Next, we're moving on to the next tuple set, which is Q7, Q3, for which we've got the values Q6, Q2 and Q2, Q6. So we know it is non-equivalent tuple set. So we are marking it as non-equivalent. Now we are moving on to the next tuple set Q7, Q4. The transition functions gives the values Q6, Q7 and Q2, Q5. Here we know that Q2, Q5 is non-equivalent and hence we are going to mark it as non-equivalent tuple set. The next tuple set is Q7, Q5 and we've got the values Q6, Q2 and Q2, Q6. And we know that Q2, Q6 is non-equivalent and hence we are marking Q7, Q5 as non-equivalent. And now we are moving on to the last tuple set in the first iteration, that is Q7, Q6, and we've got the transition functions Q6, Q6 and Q2, Q4, out of which we know Q2, Q4 is a non-equivalent tuple set and hence we are marking Q7, Q6 as non-equivalent as well. Now we have to iterate the process for the remaining unmarked tuple sets. So the first unmarked tuple set in this iteration is Q4, Q0, for which we have got the transition values Q7, Q1 and Q5, Q5 for 0 and 1 respectively. Now we can find that we still can't mark Q4, Q0 as non-equivalent tuple sets because neither Q7, Q1 is marked nor Q5, Q5 is marked as non-equivalent. Though Q5, Q5 is marked as invalid, it is not non-equivalent tuple set. Now we look into the next tuple set Q5, Q3. And from the transition function, we've got the values Q2, Q2 for 0 and Q6, Q6 for 1. Still, we can't mark Q5, Q3 as non-equivalent tuple sets. Now we move on to the last tuple set Q7, Q1. For Q7, Q1, we've got the values Q6, Q6 for the input value 0 and Q2, Q2 for the input value 1. So Q7, Q1 is also left unmarked. Now, after 2 iterations, we found that no more marking is possible in this table. So we can get into the conclusion that Q4, Q0, Q5, Q3 and Q7, Q1 are equivalent tuple sets. Thus, Q4 is equivalent to Q0, Q5 is equivalent to Q3 and Q7 is equivalent to Q1. This is the transition table for the given problem, in which we have to combine Q0 state and Q4 state as Q0, Q4 and Q3 state and Q5 state as Q3, Q5 and Q1 state and Q7 state as Q1, Q7. Strike out the individual states Q4, Q5 and Q7 so that we can combine Q4, Q5 and Q7 states with Q0, Q1 and Q3. So we have to combine the states and we have combined by writing Q4 wherever we find Q0 and Q0 wherever we find Q4. And similarly, we have to write Q3 wherever we find Q5 and Q5 wherever we find Q3. And we have to write Q1 wherever we find Q7 and Q7 wherever we find Q1. After combining the states, we get the minimized DFA table which has the values Q0, Q4, Q1, Q7, Q2, Q3, Q5, Q6 as the new transition states. Now we can construct the minimized DFA from the minimized DFA table. Here Q0, Q4 will be the starting state, as Q0 is the starting state in our problem. And Q2 will remain the final state as it is stated in our problem. So for the state Q0, Q4, the transition function gives the value Q1, Q7 on the input 0 and Q3, Q5 on the input 1. So Q0, Q4 on the input 0 goes to Q1, Q7 and on the input 1 goes to Q3, Q5. Then for the state Q1, Q7 on the input 0, the transition function gives the value Q6, and for 1, the transition function gives the value Q2. So Q1, Q7 on the input 0 goes to Q6 and on input 1 goes to Q2. The next state Q2 on the input value 0 goes to Q0, Q4 and on the input value 1 goes to Q2, which is a self loop. So Q2 on the input value 0 goes to Q0, Q4 and on the input value 1 it is a self loop to Q2. And the next state Q3, Q5, for the value 0 it goes to Q2 and for the value 1 it goes to Q6. So Q3, Q5 on the value 0 goes to Q2 and for the value 1 goes to Q6. And Q6 is the last state. For this state, on the input value 0, it goes to Q6, which is a self loop, and on the input value 1, it goes to Q0, Q4, which is drawn over here. Q6 on the input value 0, which forms a self loop, and on the input value 1, it goes to Q0, Q4. Thus, the complex DFA, which consists of 8 states, is minimized to DFA, which consists of 5 states. This is called DFA minimization. Thank you.